Section 4.2, Homeomorphisms. One of the big questions in topology is whether two given topological spaces are essentially the same. And what we mean by essentially the same is, as sets, do the two spaces have the same number of elements, maybe just with different names given to those elements? And then, in terms of their topologies, do the open sets in one space basically correspond one-to-one with the open sets in the other space? And so, one way to formalize that intuitive idea is in definition 4.14 here. Let x and y be topological spaces, and let f from x to y be a bijection, which just means an invertible function, with inverse f inverse from y back to x. If both f and f inverse are continuous functions, then f is said to be a homeomorphism. Okay, so these two functions in both directions being continuous, that's what says that the open sets in x are basically the same as the open sets in y, or they have a one-to-one, they're in one-to-one correspondence. All right, if there exists a homeomorphism between x and y, we say that x and y are homeomorphic or topologically equivalent, and we denote this with this symbol. All right, now homeomorphic spaces, there may be just one homeomorphism between them, or there may be a whole bunch of them. Homeomorphic just means there exists at least one homeomorphism. All right, well, let's look at one of the simplest possible cases. Exercise 4.22. Consider all the possible topologies on the two-point set X consisting of elements A and B. Indicate which ones are homeomorphic. All right, so first we have to figure out what all the topologies are in this set. And we know that a topology has to contain the empty set and the entire set X. And it turns out that there are sort of four collections of subsets of X that we can build up that contain both of these. And the only thing that makes these differ is which of the one-element subsets do they contain. Right? T1 contains neither, T2 contains the singleton A, T3 contains the singleton B, and T4 contains both of those, and therefore contains all of the subsets of X. Okay. Well, you can check that these collections of subsets, each of them is closed under unions and intersections, so they all form topologies. That wouldn't necessarily be true in general, but in the simple case it works out. Okay, so we have to decide which of these four resulting topological spaces are homeomorphic to one another. And well, here's one way to think it through. Homeomorphism between topological spaces puts their open sets into bijective correspondence, into one-to-one correspondence. Okay. So in particular, these spaces have to have the same number of open sets. And well, we can count them up. Right? This has 2, 3, 3, and 4. So the only possible pair of homeomorphic spaces are the ones where we give X the topology T2 and the topology T3. Okay. Now, to verify that those actually are homeomorphic, we have to construct a homeomorphism. And here's one that works. F from X with T2 topology to X with T3 topology. Well, remember, all we have to do is say sort of what the function is from X to X, right? And X just consists of these two elements A and B. So to define F, I can just say what it does to A and B, and it's just going to switch the two elements. Kind of looks like what should happen, right? Okay. And then just to check, the inverse of that function would be itself, right? Because if you do that function twice, you get the identity on X. And then to see what it does to the open sets, we have this picture here. And so F is mapping from this version of X to this version of X. And you see the empty sets here, and then T2 has the singleton A and then the whole set X. T3 has the singleton B and the whole set X as its open sets. And the function is basically, remember, sending A down to B and sending B up to A. It's interchanging the two elements. And you see that, okay, this open set here at A ends up being the open set consisting just of B, and X gets mapped to X, which is still open, and the empty set is still empty and still open over here. So the open sets do correspond to one another under this function f. All right, so that does it.